Good evening. Welcome back to the module Communication Theory Learning Outcome 1. In the previous video, we studied about the standard deviation, multivariate expectation, and the sample mean. These are the some of the properties in the statistical average of the random variable. Standard deviation means how much the values of the random variables deviated from the mean of the random variable. The deviation is observed by standard deviation, one of the parameter in the random variable. Multivariate expectation means when the function having two or more random variables, then we can able to find out the multivariate expectation. Then we studied about the sample mean of the random variable. It is calculated from the set of sample values of the random variable in an experiment. So today's session we are going to discuss about and another interesting topic in the communication theory, that is classification of random process and its properties. So random process, an idea of a mathematical model used to describe a physical phenomena. For example, we can say the weather condition is the example for random process, and another example the population survey, then random process, and then the disease spread is another example for random process. Why we are telling this physical phenomena is random process means these physical phenomena, weather condition, and the survey of the population and disease spread, these are all depend on the time. For example, the weather condition morning 10 o'clock, the temperature is 20 degree means, and then at 11 o'clock, we can't predict what will be the temperature. So that is a random process. That's why we are telling the weather condition is a random process. It is a random number. Any value will be occurring at any time. So basically, the physical phenomena, we are using the two mathematical models, such as deterministic and stochastic. So in deterministic, there is no uncertainty about it's a time dependent behavior at any instant of time. Okay, which means that so the deterministic signal, there is no uncertainty, there is no random at any time dependent behavior. Then coming to the stochastic is a random process. So in that case, the probability of the future value will be predicted between the two specified limits. So example for stochastic process, radio communication systems. So because in the radio communication system, or we can say wireless communication system, the received signal is always random in nature. At every time, every instant of time, the received signal is a random in nature. So we can call it is a random process or stochastic process. So the random process has the two properties. Such as it is a function of time and it is a random. Okay. So the formal definition for the random process, a sample space or ensemble which is composed of functions of time is called a random process or stochastic process. So, so a sample space which is composed of the set of functions, the function is with respect to time is called the random process. And there is a difference between random variable and random process. The random variable means the outcome of a random experiment is mapped into a number or value is called random variable, whereas random process, the outcome of a random experiment is mapped into a waveform that is function of time is called random process. We can see from this diagram, and there is a sample space S, which contain there are n number of outcomes in this sample space, S1, S2, Sn, and each of the outcomes are mapped into sample function, mapped into the waveform. Okay, so so we are getting the random process. Uh, you can see here the outcome of the first trial. That experiment is represented by the one waveform. The outcome of the second trial is mapped into the second waveform. Then the last, the outcome is mapped into the and then the nth waveform. So like that, in random process, the outcomes is mapped into the waveforms, which is function of time. Okay, or we can call it sample functions. Okay, the outcomes of the outcomes of the sample spaces mapped onto the set of sample functions. So each waveform we can call the sample functions, and it is in that waveform. If you measure the value at a particular time, say time t1, it will give the value of the sample function. So for the first sample function, at a time t1, we are measuring the value. It is denoted by x1 of t. Okay. Similarly, at a time t2 in first sample function, the value is x2 of t. So similarly, for the second sample function, at a time t1, x2 of t. At a nth sample function, at a time t1, is x n of t. So this x1 of t, x2 of t, xn of t, the set of these values forming the random variable. Okay, because this x1 of t, x2 of t, and xn of t giving the value of this sample function. So it forming the random variables. So in this figure, we are using that several notation. So that the capital S indicate the sample space. Then the set of outcomes S1, small s1, s2 up to Sn is the outcomes in the sample space. Then the sample point is defined by a function of time t is a sample function. So here the first waveform indicate the first sample function. The second waveform is second sample function. Third waveform is this third. Then last one is the nth sample function. So mathematically, we are using the notation capital X of t comma s to represent the sample function. It is function of time t and s. Here the s indicate the sample point. It is varying within this interval minus capital T to plus capital T. Okay, the observation interval. And the ith sample function we can represent by x of t comma si, which is equal to xi of t. Okay, so this is the general notation for the sample function. Here we are specifying the particular sample function, ith sample function. So x of t comma si. So that is the difference. So for the ith sample function, the notation is x of t comma si, which is equal to xi of t. We can represent like that also. Now, from this sample function, we can the set of sample function at a kth time instant. If you measure the value at a kth time instant from the sample function, it will give the random variable. Okay. So here there is no random. It is a random process because we are not measuring at any time. Okay, it is a random. The sample function is the random process. Okay, if from this random process, if you want to measure the value at a particular time, for example, t equal at kth time, then the random process give the random variable. So because of there are set of sample functions in that experiment, there are set of n number of sample function. So we are getting the set of sample function at a kth time instant, which constitute a random variable, okay, such as x1 of tk, x2 of tk, and xn of tk. So the difference you can see from this notation, here we are not specifying any time. That's why we are telling it is a random process. But at a particular time tk, the random process becomes the random variable. This is the random variable, this is the random process. So that is the main difference. And usually for convenient, in the many textbook, they are following x of t to represent the random process by omitting the s. Actually, you can see here the x of t comma s is the actual notation for the random process. That here the s indicates the sample point. But for convenient, we are using this notation x of t to represent the random process. So we can see another type of stochastic process. Okay, a random signal is the manifestation of a random electrical process that takes place over the time. Okay, this is another definition for the random process. Okay, is the manifestation of a random electrical process that take place over the time. Okay, then the random process encountered in communication system having the property of stationarity or ergodicity. So we'll see in detail what do you mean by the stationarity in the random process. When the random process become stationary, okay? Because generally there are two type of random process, stationary and non-stationary random process. Then it gives the meaningful relationship between statistical properties, time averages, and spectral analysis. So this is the another definition for the random process. With x of t be an ensemble, or we can say the random process of time functions together with a probability rule that assign a probability to any meaningful event associated with an observation of one of the sample functions of the random process. Okay, that is another definition for the random process. Now coming to the stationarity, okay, we can say the random process is stationary. Okay, when the statistical characterization of a real-world random process is independent of the time at which the observation process is initiated, then we can say the random process is stationary. Okay, then which means that if the observed random process is independent of the time, then it is that's the time invariant. The process random process is time invariant. Then we can conclude the random process is stationary random process. Okay. So how to check that property means you can see here the random process divided into the number of time intervals segments, number of time interval segments. Okay. Then if each segment of the process exhibit essentially same statistical properties, then it said to be a stationary. Okay. We'll see the condition for the stationarity of the random process. For that, let us take there are set of random variables. So this is not random process. X of t1, x of t2 up to x of tk denote the random variables observed by obtained by observing the random process x of t at a time t1, t2, tk respectively. Okay. So here the random process is x of t. From this random process x of t, we are taking the values at the time t1, t2, and tk. It will give the random variables x of t1, x of t2, and x of tk. Okay, then from this set of random variables, we can find out the corresponding joint distribution function of these random variables, which is f x of t1, x of t2, up to x of tk. Now, shift all the observation time by a fixed amount of time tau. Okay, so in order to represent the random variable by t1, we can replace t1 by t1 plus tau. Okay, that is the fixed amount of delay tau. So that we are getting the another set of random variable, that is x of t1 plus tau, x of t2 plus tau, up to x of tk plus tau. This is another set of random variable observed after shifting some amount of time tau. Okay, then now we can observe the corresponding joint distribution function for the set of random variables with some shifting in the time. So we are getting that joint distribution function f x of t1 plus tau, x of t2 plus tau, and up to x of tk plus tau. Then after getting the joint distribution function for both the set of random variables, now we can check the random process whether it is stationary or not. Okay, uh, the random process x of t is said to be strictly stationary if the joint distribution of the set of random variable with shifting is equal to the joint distribution of the set of random variable without shifting. If both are equal, then we can come to conclusion the given random process is the stationary random process. So here we are checking by using that joint distribution function of the random process. Let put at k equal to 1 because the k means the time. So at k equal to 1, we are getting the distribution function f x of t1 of x1 equal to f x of t1 plus tau of x1. Okay, so which means that with the time shifting, the distribution with the time shifting is equal to the distribution without time shifting. Okay, it is independent of this delay tau. So we can say that the first order distribution function of a stationary random process is independent of time. Is independent of time. Okay. Next, now consider k equal to 2 and tau equal to minus t1. Then you can substitute k equal to 2 and tau equal to minus t1 in that previous equation, this equation. Okay, we can get this equation f of f x of t1 x of t2 equal to f x of t1 plus tau x of t2 plus tau. But here tau equal to minus t1, so t1 minus t1 equal to 0. So we are getting f of x of 0 x of t2 minus t1. So here also tau replaced by minus t1. So the observation from this second expression is that the second order distribution function of a stationary random process depends only on the time difference between the observation times and not on the particular time at which the random process is observed. You can see here the from the second order distribution function, this joint distribution function does not depend on the observed time. It is only depend on the difference between the two observed time, t2 minus t1. Okay. Next, coming to the ensemble. Ensemble also we can call the random process. Okay. Another name for the random process is ensemble. A random process maps experimental outcomes into a real functions of time, like that waveforms. The outcomes is mapped into the waveforms. The collection of time functions is known as an ensemble, and each member is called sample function. Okay, then the ensemble usually represented by the notation V of t comma s, where t is the time and s is the ensemble member of sample function. So these points I collected from the our textbook, because we are following the two textbook. One is the Simon Hiking. Okay, both book we are following. Then the example for the random process, the set of voltage waveforms generated by the thermal electron motion in a large number of identical resistors. So you can pick a resistor at a random and then observe the waveforms. Is the example for the random process. Okay. So the particular outcome is mapping into the sample functions. So it is denoted by V of t comma Si are equal to Vi of t. Okay. So this is the sample function of the it's the sample function of the particular outcome in that experiment. Okay, in that experiment means that the resistor, the drawn the resistor from the box. So let V of okay. So at particular outcome correspond to the sample function. V of t comma S equal to Vi of t. But at the time t equal to t1, we are getting the value for the sample function. So this notation indicates the sample function. If you want to find out the value for this waveform at a time t equal to t1, okay, we can observe that the value, okay, at a particular time. So therefore, at the time t equal to t1, we are getting the value for this sample function. That is v of t1 comma si, or which is equal to vi of t1. So, so you can see here the v of t1 comma s denoting the random variable v1, which is defined by a vertical slice through the ensemble at t equal to t1. Okay, actually the waveform is next slide, voltage waveform. So this is the set of voltage waveforms obtained from the outcomes of the resistors. Okay, so the waveforms in an ensemble V of t comma s, ensemble means random process. Okay, there are n number of sample functions or voltage waveforms from this experiment, such as V1 of t, V2 of t, and the Vi of t. Okay, the each sample functions are waveforms varying with respect to time. That's why we are telling it's a sample function. It's a function of time, and we can see here from the first sample function, that is v1 of t. We can at a time t equal to time t equal to t1, we can get the value for the sample function v1 of t. At a time t1, we can get the value for the sample function v1 of t. Say v1 of t1, and it is defined by v1. It's the random variable. Similarly, at a time t2, we can get the value for the sample function v1 of t is defined by v2. So this v1, v2 called random variables of the sample function v1 of t. The same way, we can see from the set of waveforms at a time instant t1. Okay, from the first sample function or first waveform, we are getting the v1 of t1. From the second waveform, v2 of t1. From the last waveform, v of t1. The set of these values v1 of t1, v2 of t1, v of t1 is forming the random variable v1. Similarly, at time instant t2, V1 of T2, V2 of T2, and Pi of T2 forming the random variable V2. Okay, so the V1, V2 is the set of the values of the sample functions. Okay, that's the point here. It is explained. Similarly, the vertical slice at a time t to define the another random variable v2 from all the sample functions. So therefore, the random process boiled into the family of random variables. So we can understand the difference between the random process and the random variable. If you observe the value at a particular time, then the random process becomes the random variable. So here also is the same thing. We can have to, for convenient, you can change the notation from v of t comma s into v of t, the random process notation. Okay. Then we can find out the mean value for the random process v of t at arbitrary time t. Okay, which is equal to expectation of v of t. The same procedure here also we are following how we are estimating the mean value for the random variable. The only difference here, the random process is function of time. Okay, v of t. We have to take the expectation for this random process v of t. So here the expectation of v of t denote the ensemble average obtained by averaging over all the sample functions with respect to time t. Okay, okay, which means that here the v of t is not only the single sample function. There are n number of sample functions, n number of waveforms. Okay, then from all the waveforms, we can find out the average value. It will give the main value for this random process v of t. Then if you observe the value at time t equal to t1, then the mean value expectation of v of t1. Here we are not mentioning the time t1, but here we are mentioning time t1. So it becomes the random variable. Okay, then the expectation of the v of t1 equal to v1 bar means the mean value of the random variable v1. And this mean value of the random variable v1 at a time t1 is differ from the mean value of the random variable v2 at a time t2. Okay, so for each time instant we are observing the random variable, and there is we can't say the mean of the both random variables are equal. Then the relation between random variable v1 and v2 is defined by autocorrelation function. The notation is RV of T1 comma T2. So because the first random variable is observed at a time T1, the second random variable observed at a time T2. So the autocorrelation function of V1 and V2 is expectation of V1, V of T1 and V of T2. Okay, because there are two random processes, V of T1 and V of T2. If V1 and V2 are statistically independent, okay, now then the autocorrelation function of these two random variable is the product of the mean of the each of the random variable, that is V1 bar, V2 bar, right? So here we please understand the notation. Here we are using T1, so it becomes a random variable. If it is T means a random process. And if T1 equal to T2, the both T1 T2 are equal, then V1 equal to V2. In that case, the autocorrelation function reduced to V1 squared bar. Okay. Now we can consider the transformation of the random variable, random process. Like in random variable, we studied the transformation of the random variable. Like that, in random process also, there is a transformation in the random process. So the random variable VA equal to G of X comma TI means the random variable V depend on the another random variable X and the time parameter T. Okay, so in this function we can find out the mean value for this transformed random process if we know the PDF function of the random variable x. Okay, so if we know the PDF function of the another random variable x, then we can able to find out the what is the mean value for this random variable vi. Okay, so then we can find out the mean value for the function g of x comma ti, that is expectation of g of x comma t equal to the same formula what we are using for the random variable minus infinity to integration minus infinity to plus infinity g of x comma t p of x ds, where p of x is the PDF function of the random variable x. And similarly, we can find out the autocorrelation function for the function g of x comma t, that is a transformed random process. Okay. So here also we are using that the PDF function of the random variable x, px of p of x, to find out the autocorrelation function. Now we can take the two random process v of t and w of t. Okay, there are two random process. Both are different. Then for this random process, we can find out the cross correlation function. Okay, the cross correlation function of this two random process v of t and w of t is denoted by r v r vw of t1 comma t2, because both are different random process, and which is equal to expectation of v of t1 and w of t2. So we are getting that cross correlation function which is equal to v of t1 bar w of t1 bar. Okay. Then we can find out the covariance function between two random process v of t and w of t. We are representing by c ub of t1 comma tt. The c indicate the covariance, r indicate the correlation. Okay. So the variance formula we know for the random variable, how we are using the variance. Same formula here also we need to apply expectation of v of t1 minus expectation of v of t1. Okay. Similarly for the another random variable, then if you have to cross multiply, okay, if you cross multiply, we can get the simplified expression for the covariance of these two random process v of t and w of t. So which is equal to expectation of v of t1 w of t1 minus expectation of v of t1 into expectation of w of t2. So this is the mean of the random process v, this is the mean of the random process w, but this is the autocorrelation. Autocorrelation of the means cross correlation of the random process v and w. So we can replace the first term by r vw of t comma t1 comma t2 minus v of t1 bar w of t1 bar. But this cross correlation we already found here. It is a v of t1 bar into w of t2 bar. You have to substitute here, so it becomes 0, which means that the two random process having the process have the zero covariance, means both are uncorrelated to each other. Both random processes are uncorrelated to each other. Okay, and then and one more property is if two random processes said to be orthogonal if the cross correlation of these two random processes is equal to 0, then we can say that both random processes are orthogonal to each other. So that orthogonality condition will be checked by the cross correlation of these two random processes. And if whether there is a correlation between the random process, okay, that will be checked by finding the covariance of the two random process. Right? So today's session we studied about the random process, then some of the properties in the random process such as autocorrelation, cross correlation, and covariance. Okay, thank you.